Welcome to Streaming 102. We're going to be covering stream graphs and how they work in streaming systems. If you were here last week, you've seen the same slide. My name's Josh Fisher. I am a team lead here at 1904 Labs in St. Louis, Missouri. I am also a Apache committer and a project management committee member for the incubating Project Heron, and I wrote a book. The book I wrote along with Ning Wang is called Grokking Streaming Systems, and we're going to talk about some material that is on here today. So there's three main topics that I want to cover tonight, or talk about, and one of them is streaming isn't always a straight line. And what I mean by that is there's different scenarios where you're going to have to process data in a non-sequential way, and we will get into the details here in a little bit, and then we're going to talk about ways to make that processing more efficient, and then also what to do next after this talk. So in chapter 4, I believe it is, we start talking about this fraud detection system that we're trying to work on, right? So there's the business use case is that there is a system that accepts transactions that can come from browsers, it can come from physical locations, which are like stores, physical brick and mortar locations, and then mobile devices. And then those transactions will then be put into the cloud. Then the cloud will then, that magic poof will then present those transactions to the paying bank saying, hey, somebody wanted to buy something at this merchant for this amount of money. And we think it may be fraudulent or we think it may not be fraudulent, but here you go. Here's all the data we have on it. You could then make a choice to pay this transaction or not. So that's a very high level of the scenario, right? So brick and mortar locations, web pages, mobile devices, so forth, they pass into the card network and then they hit the bank. And then the bank will then give a response back whether to pay or not. And if you think about it in real life, if you go and you buy something anywhere, this whole process takes, a second or two at the most, the whole round trip, right? So, this isn't something that you want to wait 5 minutes for. You don't want to swipe your card and then wait 5 minutes for the thing to clear. So everything has to be very fast, very efficient. So in our last job, we had a couple of components that were one after another, right? So they were, you'd hit a source and then you'd hit, I guess the example was we had a sensor reader and then we had a counter, right? So the sensor reader read the data in and then the counter counted the vehicles. If we were to add another component in that fashion, it would come after the vehicle component counter. So the job we have for you here is structured similarly to the one last week, right, or 2 weeks ago. So we have a transaction source that's going to be pulling data in from the outside world. This will be from websites, mobile devices, and brick and mortar locations. And then we have these things called analyzers. In this case, we have 3 of them, which will do some fraud detection logic, and then we have a component at the end that'll aggregate all the scores of the analyzers to say, hey, banks, these transactions are fraudulent or not. The problem with this setup is that in the real world, credit card processing is very, very complicated, especially fraud detection. And there's always some new scheme coming out, and companies need to be able to modify fraud detection rules on the fly. And let's say a company, creates, 10 rules one year, 10 rules another year, and next thing you know, they got 20 rules they got to go through. And each time they add a rule to this job, it would take longer to process. So a more efficient way or streamlined way is to kind of fan out this transaction that comes into the job, right? So on the job to the left, you see we have 5 steps that this thing would have to go through one at a time. So transaction source, average ticket analyzer, windowed proximity analyzer, windowed transaction count analyzer, and score aggregator. And as you added more components, this job would take longer and longer to process. And so you as the user, if you swipe a card, it would take longer and longer for you to buy something. So another way we can get around this is we can use things called fan outs or fan ins, keeping all this, and I guess I should say ahead of time, this is a streaming framework generic discussion, right? So these concepts that we're talking about today, you can apply to any streaming framework. We're just not going to use the same lingo across each different framework. So Flink may call it one thing, Pulsar may call it something else, Heron may call it something else, etc. So for the purposes of this conversation, we're talking about fan out or fan in, and I'll come back to this in a minute. Yeah, let's go and kick over to the next slide. To talk about the total flow of this transaction, to give you a little bit more complication to pay attention to what I'm talking to tonight, is that when a user swipes a card, whether it's through whether it's a brick and mortar location or they input it in a website, they input it into a mobile device, it's going to make this big long trip, right? And so we're going to kind of break down some of the steps. Hopefully, I can make it as clear as possible. So one, as soon as a card is swiped, it's going to enter the API gateway. That's step one. And that API gateway is going to forward that transaction on to the transaction presenter, and that presenter is going to hang on to the transaction for a short period of time before it presents that transaction to the bank. And the reason for this is that at the same time, in another thread, the API gateway dumps that transaction off into a fraud detection job, or at least puts it on a queue for a fraud detection job to process. And what's going to happen is the transaction source is going to pull that job in. It's going to run the transaction through a set of rules, and that's going to aggregate the score. It's going to take all the different fraud scores from each one of those analyzers. It's going to dump it into a database to then be pulled out by the transaction presenter and then present it to the bank. And then finally, with this fraud score, and we'll get into a little more details what that fraud score is, the bank can then make a decision on, hey, I want to pay this transaction or I don't. Finally, that response is then sent back, and then you as the user, you find out if your card is approved or declined. So a little bit more details about this job. We talked about before data sources. This is the same thing. So we talked about data sources in the last talk 2 weeks ago, right? And so we had it's a very similar concept. We have a transaction source, which is pulling transactions out of that API gateway to then be dumped into a job. The details, and I'm not going to get too much into the core logic of how this works, but we're talking theoretically here at the moment that we have an average ticket analyzer that's going to be checking the average spending of a user across the lifetime of their account, we'll say. So let's say on average a customer of the bank spends between $1 and $100 per transaction. You could think of a transaction that would come in at $3,000 to be potentially fraudulent. The window proximity analyzer here on the right of that component is a component that would look for large jumps in physical location of the card being swiped. So this may not apply for every job, but for every transaction swiped. But if a user was in St. Louis at a certain period of time, they swiped a card to buy a Pepsi from 7-Eleven or some gas station, and then they hopped over 3 states 3 minutes later and spent the same amount of money on a different soda in person, that would be a problem. So that is what the proximity analyzer is looking for. And finally, we have another one that's a windowed count transaction analyzer, and I'm not going to get into windows for this talk, but basically, this analyzer is cutting up a never-ending stream of data, right? Because streaming data never ends. It's cutting them up into slices of time, and it's checking for repetitive transactions across the same cards. And some of this is fictitious, but we're just trying to build some context. Finally, the score aggregator is going to pull the fraud scores that are marked in each one of those analyzers and then dump them into a database for the transaction presenter to pull out. So there's a few new concepts since the last talk we did that I'd like to talk about, and one of those is upstream and downstream components. So if you look at this job here on the right, the average ticket analyzers, if you look at all three of the analyzers, those are the downstream components of the transaction source. In a flip fashion, the transaction source is an upstream component of all the analyzers. Another example is that score aggregator is a downstream component of all the analyzers, and all the analyzers are upstream components to the score aggregator. And this is where we're going to get into stream fan in and fan outs, and then we're going to talk a little bit about graphs and then DAGs. So typically in most streaming systems, I can't say all because there's always going to be somebody that proves me wrong, the jobs are represented as directed acyclic graphs. It's a mathematical term. Basically, the graphs, if you look on the left, I have an example of a graph, right? And this graph shows vertices that are connected by edges but there's no real show of how data flows through this graph. It can go either way. There's no real way. So this is just how this is a graph, right? And then over here on the right we have a directed graph, and you're looking at I just dropped an arrow on C down here. The difference between this directed graph is that you have components that are linking to each other, right? So C, D, and E both can make a circular fashion, and so this is a directed graph. And then finally, we have here at the bottom a directed acyclic graph. I'm missing an arrow, so you're going to have to bear with me. A directed acyclic graph is typically what we use to represent streaming jobs. This isn't the case for all, but typically this term is used because they're acyclic, because there's no way you could, if by definition, if you went from component A here on that directed acyclic graph and you went down any one of its edges, you could not get back to A. Now, somebody's going to argue and say that is possible in some streaming frameworks. It is, but that is the term we use, and that's the term we're going to use for this talk, is directed acyclic graph, or DAG. So we talked about the job, we talked about the scenario, we talked about the different ways to represent the job that we're working through. So a way to make this job more efficient, or at least the first pass of the job to make it more efficient, is we have, we basically, for lack of a better term at the moment, we parallelized out those different analyzers, or we're running them concurrently, right? And so what we're doing as programmatically is the transaction source is taking transactions in, and it's replicating or it's duplicating the same event to each one of those analyzers. The problem with this is that typically credit card transactions come with a lot of data. You have to know how, you have to be able to check if they are fraudulent. You have to be able to, there's lots of rules. I'm not going to get into all the details, but they're big payloads, right? And so duplicating data across each one of these analyzers causes an I/O problem. All right, so yeah, if you see here in the diagram, we have the fan out. We also have some code here listed at the bottom that we have a SDK. I shouldn't say an SDK. We have a small framework we programmed for you, or we created for you, that you can do some testing. And basically, the way Ning wrote this framework is that you can basically run any streaming engine or any small streaming job on your local. Very easy to learn, very easy to use, and it'll really help you kind of work through the book. So in this case, this transaction source has an out, and it's basically applying operators to each one of those streams, so they're getting duplicates of the same data. So each transaction that comes in at this time is duplicated by 3, which causes memory issues, or which could cause memory issues at some point. So if you look at detail here, this arrow, no matter what component downstream is pulling from, they're all pulling from duplicated events. So all 3 of those queues are consisting of the same events at any point in time. So there's duplicated data across all 3. Now, another way we can do this is we can do a fan out with different streams. And if you think about efficiency, you can think about the use cases of each one of these analyzers. Not all of these analyzers are doing the same thing, right? So average ticket analyzer is looking for the average spending limits of a user. Proximity analyzer is looking for large leaps in latitude and longitude. And then windowed count transactions are looking for number of transactions in a specified time. All of those are using different data. So a way to make this more efficient is to only pass down the data that we need to each analyzer, potentially reducing, I shouldn't say potentially, you will reduce the resources needed to transmit that data across different streams. So on the first version up top, I have an arrow, yeah. We have the transactions are all duplicated. So each one of those analyzers are getting copies of the same data. In the second version, we have each analyzer is getting its own copy of the data, or only the data it needs. And really, it could be the same event if we really wanted to, with just a bunch of null fields, with the exception of the fields that are required for each analyzer. Right, yeah, so if you see here in the first one, just to show some differences, in the first version of the job, the queues would all have the same set of events, with the same data structure. In the second one, we have different sets of data, or different pieces of data off of each of the same So we have different sets of data based off the same transaction that are only pertinent to those analyzers, which allows for more efficient data transmission. Another way we can do this, or in a way we do this, is by channels, right? So a streaming job that you can define which data goes where. And by doing that, you as a developer can really take control or granular control of how your job processes data. And you can call these channels whatever you want typically. One of them would be location based, one of them would be count based, or and so forth. You can name whatever you wanted. And right, so here we have an example here in the Streamwork code that we wrote for you, or that Ning wrote for you. In this case, he sets up here on this event collector as a location based channel. And that location-based channel is specific to the location, a location event that is passed to a windowed proximity analyzer down here at the bottom. And each one of these will get their own different events so that the job can process faster. We were hoping for, right? Now, the stream fan-in is a little bit different, right? So we have different pieces of data coming from each that went into each analyzer, but each analyzer is then producing a score, a score of 0 or 1 to say this transaction is fraudulent or not, or at least we think it is, right? And what these analyzers are all going to be producing is the same type of data that you could basically merge together on the transaction ID. So each one of these analyzers are going to give out, in this case we call them eval scores 1, 2, and 3. Those are just, hopefully you don't hear the dog. Those eval scores are, they're all specific to the analyzer for a specific transaction. And what we're going to do with that score aggregator is we're going to merge in all those evaluation scores, and we're going to make a score of, which in this case would be 0 to 3. 0 being probably not fraudulent, and then 3 being the most probably fraudulent. So the way this works in our engine, in this, the small little thing we built for Grokking Streaming Systems, is each component will push out its events into a single queue, and then that single queue will then be ingested by the score aggregator. So it's just pulling off one thing, and what it'll do is it'll look for events that have the same transaction ID and then add that score to it, whether it's a 1 or a 0, and then it'll have a total fraud score for that transaction. It'll dump it off into the database. Now there's another type of stream fan-in which I didn't cover for this job, which can be a little trickier. But another fan-in is called the join, and this is a whole nother discussion we could get into. But the merge that we talked about earlier, we were merging the same types of data, which I probably should have visually shown you, but was basically consisting of transaction ID and a fraudulent score and a fraud score, right? And when you bring together the same types of data, that's a merge and a framework agnostic term. Another framework agnostic term is the join, right? So much like a database, you can join tables of different structures based on some key. Just in streaming, you can also join data in real time, different sets of data in real time based on some type of key. So if you look, hopefully I got some arrows, I do, good. So if you look up here at this top object, we have a user ID 001 with name of Tim. And then we also have another object over here coming user ID 001 with a phone number of 12345. And then finally at the bottom, we can join that data in real time to create a new object. So here's what to do next. My friend Ning Wang took a tremendous amount of time to build a streaming framework that you all could learn from while reading our book, or even without the book if you wanted to. But he really spent some time to make this framework agnostic so that you could learn any of the core concepts of streaming from this book and from this framework, and apply them to any streaming system you want to learn, virtually any streaming system. And the goal is that you as the developer can level yourself up and learn the next piece of technology. Please check out his code base. It's on GitHub, github.com/NingWang/Grokking Streaming Systems. He's done a fantastic job putting it together. I've been super lucky to work with him. If you're looking up your job, up your career in streaming, please check out this framework or this code base. So getting started, you would just check out the Git URL. This job in particular can be ran by the commands in terminal too. He's got instructions in the README, but he went through and he created several different options and several different jobs you can run within the framework. So this one in particular is called, it's called the fraud detection job. And the way to run that after you build it is, you can see it down here at java-cp target/gss jar, and then you'd run the main class, which is com.streamwork.chapter4.job.fraud detection job, and it'll run the job for you. But first, you're going to have a listener open in terminal 1 on port 9990.